Okay, everybody, we are in the home stretch here for the extra topics for Chapter 17 that are not found in our textbook. This one, as you can see, is function operations, not to be confused with function transformations. We saw those previously. That involves changing the function equation and how that relates to a change on the graph. This is function operations, and while it does have a little bit to do with a graph, and we'll kind of take a peek at that at the end, for the most part, this is just about algebra. As are the next two topics actually that we'll cover. So today is function operations, and that's what I've got up here in green. We know what operations are, right? It's like addition, subtraction, multiplication, division, and I would add to that like exponents and taking roots, which is really just the same thing as exponents. In the next video, we're going to cover something called function compositions, and then in the final one, we'll discuss function inverses. Compositions and inverses, a little bit more challenging. Today's topic really is pretty easy. I'm being honest about it. We're just going to take functions and we're going to add them, subtract them, multiply them, divide them, and raise them to powers. So let's go. Here's just some notation that I want you to be familiar with. If we want to take a function f of x and then add it to a function g of x, often we use this notation to describe that. We just put the f plus g in a parentheses and then the x. Same thing with the minus. Same thing with the times. Sometimes there'll be a dot in between the f and the g, but not necessarily. For a quotient, we'll just do f divided by g of x. Okay, so those first four, I think, should be pretty straightforward. Just want you to be aware of, what it means. If you see this thing on the left, it just means this thing on the right. I think you got this. Now for exponents, we're going to use this notation here. We're going to put the f of x all inside of a separate set of brackets and then put the exponent outside of it. So this means f of x times itself however many times that exponent says to do. Now this notation down here, I say it kinda depends. So there are some books and some websites out there that are going to use this notation to mean this notation. So for example, I'm going to say that this is the function f of x squared, and some books and websites are going to say that's also the function f of x squared. And there are some contexts where I will tend to write exponents in that form. For example, when we deal with trigonometric functions, it's very common to write it like this. This means the sine of x all squared. We'll cover that in a future chapter. Don't worry about what that is right now. But the reason that I'm going to insist that we use this way of writing it is because of inverses, which we'll see 2 videos from now. And we've actually talked a little bit about inverses with trig before. You remember the inverse trigonometric functions were written in this form. And that -1 we said was not an exponent. It meant we were using the inverse sine function. And so in the same way here, if I write f to the -1 of x, that's an inverse, which is not the same thing as if I write f of x all raised to the -1, that's an exponent. So we see that this notation can be potentially confusing and a bit ambiguous. So for our course, we're going to use that for exponents with the one exception of trig functions, just because it's super common to write out sine squared and cosine squared, etc., with the exponent right next to the sign. But anyway, like I said, we'll talk about that later. Let's just move forward with this easy stuff for today. Okay. Oh, one more thing about exponents. Having the exponent on the x is absolutely not the same thing as having the exponent on the f of x. Don't worry about what kind of change it is, because it's going to depend on what the function is and what the power is, but the point is they're totally different things. Just as an example, here's a function. Here's what happens when I change the x's into x squareds. Here's what happens when I take the function and multiply it by itself. Remember, we're doing x squared plus 2x times x squared plus 2x. So we're multiplying a binomial times a binomial and then combining the like terms. And it would be tempting to think that like, oh, this is affecting the x, so this should be some sort of a horizontal change, whereas here the square is affecting the f of x, so that should be some sort of a vertical change, since that's what we saw with the structure of function transformations. But the truth is, this is just like we're taking a quadratic function and in both cases turning it into a quartic function. So we're really changing what the function is. So I don't want you to think of it in those terms. In fact, here, let's look at some graphs. So here's our original function, and here is f of x squared, which is quite a bit different. Um, it looks like it's been moved up and right and maybe been made more narrow or stretched taller, but really don't think of it like that at all. It's a completely different function type. And here is f of x squared. No, it's quite a bit more different. This one actually, I can explain to you what's going on here pretty easily. If we take the y values for any point along this curve and we square the y value, we'll get the new point here. So here we had the point negative 1, 1. If we take that y value, negative 1, negative 1, if we take that y value, negative 1, and square it, we get positive 1. So the new point is at negative 1, positive 1. The points with y values of 0 are still 0. Okay. The original curve had, let's just look at one more. Our original curve had a y, right here, negative 3, 3. And that's going to go to negative 3, 9. And this down below, we'll talk about this again in the next video. There is a difference between the dot, which means multiplication, and a circle. That will mean that we're taking the composition of two functions. But again, we'll talk about that next time. But like I said earlier, we're not going to worry about the graphical implications of this topic because they get very confusing very fast. We're only focused on the algebra. So for the next couple of examples, I'm just going to deal with these two functions, f of x and g of x, as we see in front of us. Let's do some stuff with them. So for starters, here's f of x plus g of x. We're just combining like terms. X squared plus x squared is 2x squared. The x and the negative x cancel out. Negative 90, negative 110, that gives me negative 200. Cool. And here's a couple of subtractions for you. If we want to do multiplication, that's fine. We already know how to do polynomial expansion, right? We're just going to take each term from the first one and multiply them by each term in the second one. So we should have 3 times 3 multiplications that we need to do, and then we'll combine the like terms. And I've recommended this before. I think you should group your like terms in columns. So these 3 all came from multiplying x squared by the terms of g of x. These 3 all came from multiplying the x times the terms of g of x. And then these 3 all came from multiplying negative 90 by all the terms of g of x. I want to look at a quotient now. So it would be natural to think, well, we'll just write x squared plus x minus 90 over x squared minus x minus 110. And that's fine. That's correct. But we can get more information if we factor each of these first, because that might tell us that we're allowed to cancel some things. In this case, we could cancel the x plus 10 and the x plus 10. But I've got this circled already. We need to be really careful about this denominator because what are we not allowed to divide by? 0, right? So this quotient, f divided by g, is only valid as long as x is not equal to negative 10 or 11. Otherwise, though, yeah, the quotient is just equal to x minus 9 divided by x minus 11. And as a final example, I know we already looked at one like this earlier, the difference between f of x squared and f of x squared. one is, in this case, much more simpler than the other. And really, I think in general, when we square the x, we should always get a simpler expression out than when we square the actual function, because squaring the function will result in a whole bunch of multiplications that we need to do, whereas squaring the x, we just replace the x in the expression. And yeah, I erased the work. This should be the final answer, so you can do it yourself and check against mine. I'm pretty sure it's right, hopefully. Anyway, that's really, look, that's all that today's video is about. I just want you to know the new notation so that you know when you're being asked to add, subtract, multiply, divide, or square a function versus squaring the variable. And then it's just like normal operations and then combining like terms. We don't really need to worry about anything with a graph. Like I said, that gets really complicated, too complicated for us. Yes, we may be the honors section, but even we have our limitations. Anyway, that's all. Not bad, right?